Training a large language model with 175 billion parameters requires coordinating a staggering volume of data across massive enterprise-grade hardware clusters. While foundation models are excellent generalists, they lack the precision for specialized domains. Converting a general-purpose model into a specialized medical or legal expert requires a focused training phase. Traditional full fine-tuning attempts this by updating every single parameter in the network. This forces the hardware to track gradients and optimizer states for the entire model simultaneously. For a 175 billion parameter model, this calculation requires roughly 700 gigabytes of video RAM, a requirement that keeps fine-tuning locked behind the doors of massive data centers. This chart reveals the engineering solution. With LoRa, trainable parameters drop from 175 billion to just 8 million. This slashes the memory needed for training. Full fine-tuning requires 700 gigabytes, but LoRa uses just 3 gigabytes. This approach is part of a category called parameter-efficient fine-tuning, or PEFT. By engineering a mathematical loophole around the VRAM constraint, PEFT enables consumer GPUs to fine-tune models once restricted to high-end server clusters. LoRa, short for Low-Rank Adaptation, works by applying a surgical intervention to a pre-trained network. To maintain efficiency, the weights of the original base model are completely frozen. They are never altered during the training process. Instead of modifying the foundation, developers attach trainable modules called adapters to existing model layers. Input data flows along a dual pathway, simultaneously passing through frozen weights and parallel adapters, before both outputs are mathematically summed together. Because the base model is locked, the hardware only needs to track and apply gradients to these tiny, isolated adapter modules. These adapters are usually targeted at the attention mechanism, specifically the query and value projection layers, where they can most effectively steer the model's behavior. By isolating training to these parallel patches, the system gains new domain expertise without disturbing the foundational knowledge the model learned during its initial training. This raises a mechanical question. How can a tiny set of adapter weights accurately mimic the massive network-wide update of a 175 billion parameter model? The answer lies in low-rank matrix decomposition. The size and complexity of this adapter are controlled by a single hyperparameter called rank, or R. Consider a 1,000 by 1,000 frozen matrix requiring a 1 million parameter update. We decompose this update into two smaller matrices, matrix A and matrix B. Multiplying them produces an identically sized update matrix, achieving the same structural change using only 16,000 parameters. To prevent these new adapters from destabilizing the model the moment training begins, LoRa uses a specific initialization protocol. Matrix A is populated with standard random noise. Matrix B is initialized at exactly 0. This ensures the adapter's initial influence on the network is mathematically null, keeping the model's output stable at the start of the training run. Matrix decomposition creates an elegant mathematical shortcut, projecting a massive structural update into the model using a fraction of the traditional computational footprint. Even with the efficiency of LoRa adapters, loading the base weights of a massive foundation model can still overwhelm a consumer GPU's memory. Quantized LoRa, or QLoRA, solves this by applying aggressive memory optimization to that frozen foundation model. QLoRA compresses the base weights, crushing standard 16-bit numbers into a dense 4-bit representation. The LoRa architecture remains the same. Trainable 16-bit adapters are attached to the top of this now compressed 4-bit model. To preserve the model's reasoning capabilities at this extreme compression level, QLoRA uses a data format called NormalFloat 4-bit, or NF4, which is optimized for the weight distributions found in neural networks. It further reduces memory through double quantization, which compresses the quantization constants themselves. QLoRA slashes the resting memory footprint of the weights, leaving just enough available VRAM for the adapters to handle the actual training. These memory savings come with specific engineering trade-offs that developers must consider before choosing a fine-tuning method. This chart displays the maximum model size supported on a single 24GB consumer GPU. While standard LoRa can handle a 13 billion parameter model on this hardware, QLoRA scales up to a 70 billion parameter model in the exact same memory footprint. However, this increased capacity comes at the cost of training speed. The training throughput drops from 125 tokens per second using standard LoRa to just 70 tokens per second with QLoRA. This slowdown occurs because the hardware must constantly dequantize the 4-bit weights back into 16-bit format during every forward pass to interact with the adapters. This leads to the final question. Does compressing a model to 4 bits permanently degrade its accuracy? Benchmark data reveals that accuracy remains remarkably stable. The scores for full fine-tuning, LoRa and QLoRA are nearly identical. The difference between standard LoRa and QLoRA is under 0.1%, confirming that the NF4 compression process is functionally lossless for these tasks. The final decision depends on available hardware. Choose LoRa for speed and simple implementation, or leverage QLoRA as the essential tool for scaling up to larger models on a restricted memory budget.